Hi everybody, this is Edgar, and I'm welcoming you to my DynaLoop HS, DynaLoop II HS VLF loop construction video. I'm going to try to walk you through most of this stuff. This is a VLF natural radio receiving loop. It's not really an antenna. It's made actually to receive audio frequencies that float through the air in magnetic form, which of course is most of your spherics, tweaks, and whistlers that result from lightning strikes and of course some other earth sounds. I'm in the mid-latitude, so I may not get the choruses and other effects that happen with the auroras in the northern latitudes, but all that aside, first thing I have to do is it would be remiss and negligent of me not to remind you that if you do build such a loop and put it outdoors, watch out, because any wiring you have outdoors is going to be a target for lightning. The nearest lightning strike I know of to my house has been like 3 miles away. Most people say that's alright, but it ain't, because it hit a police officer's house, blew his bathroom shower out, and caught the squad car on fire. So that's 3 miles away from my house. Yeah, I take the lightning seriously. The particular setup I use, of course, I have a loop outdoors, and my signal feed line goes through a tree, and it's hooked up to the house. It's mini coax supported by TV antenna guy wire, so it's mechanically strong and not prone to wind damage. And it hooks to the house on this hook. The hook is the same hook that's used by the phone company for the phone line. So God forbid if we ever did have a hit, because if we do have a lightning hit, this is just a simulated photograph. This is one I took off the internet of a tree getting hit, and well, I just I just drew in the feed line with my photographic program, and the feed line will of course be turned to vapor and become a side flash real fast if that tree, God forbid, ever did get hit. So yeah, lightning's serious. Here in Middle Tennessee, we don't get a lot, but especially in my neighborhood. But that police officer, after it blew half of his house up and caught the squad car on fire, I take lightning a lot more seriously. No lightning protection is 100% guaranteed. Lightning strike on the average is a pulse current of 20,000 amps, and regardless of whether it breaks through here and finds ground here, or on the earth where it's actually lying on the ground, or actually in, I don't see any of this. Let's go back here. Okay, regardless of whether it's the spot where the feed line touches the ground where it breaks through, or whether it's in the static discharge unit, I refrain from using the term lightning arrestor because nothing can stop lightning. But don't take my advice as responsible or legal. This is what I feel comfortable with, and there's nothing that will completely prevent human injury or property damage should your property get hit by lightning. If you live in a spot where you know that your neighbors have been hit or your property's been hit, I don't even recommend putting any type of signal wiring outdoors, and I'd be very wary of even using a phone in the storms. Okay, here I'm going to show the schematic of the actual electrical system within the loop. The whole loop will be built inside of 1.5-inch PVC plumbing pipe, and for the T's and elbows I'm using not the drain pipe but the supply pipe, which has a straight T and straighter elbows. So I'm trying to walk through this. This may not show up. If you have good resolution, this will show up on the video. The loop is made from 14 gauge wire. I refer to it as a 24 by 36 inch loop. Actually it's not, it's a little bigger than that. For simplicity of measurements, I call the crossways top pipe, I call it 36 inches. It's measured out to 36 inches. The side pipes, they're 24 inches. And the elbows and fittings add a little bit to that, but for calculating and general purposes, especially for measurement, it's so much simpler just to use the length of the pipes and cut them to even lengths, so I do. We use 3 turns of that number 14 wire, and what that does is that presents an impedance. Well, that's a little ahead. It presents an inductance of 16 microhenries, and at 12 kilohertz that works out to an impedance of 1 ohm. Now the transformer, the 3.2 ohm winding is what they call the secondary. I'm using it backwards. We'll call that our primary. Okay, the primary, when this secondary is loaded properly, from end to end on this secondary is 1.6 K, so that's 1.6 kiloohms, or from either end to the middle is 400 ohms, which would be great for driving 600 ohm audio inputs like on a board or on a long piece of phone line going to a VLF receiver. So we use the Tamara MET23. The MET23 is a wideband communications transformer with a response from 300 Hz to about 100 kHz plus or minus 2 dB. R1 inside across the transformer's primary is 10 ohms, and it's in conjunction with the inductance of the loop causes a fall off in response when you get high above the audio band. It tends to reduce cross modulation, interference, and other products that are a result of receiving signals that are way above the audio band. It tends to clean up stuff that's above band. Now the other resistor we have is a 2.2 meg, and it goes from primary to secondary, and that's the static bleed off resistor. Any large object, any large metal object or conductive object, when it's in free space, tends to pick up a static charge. Unterminated phone lines and power lines can pick up a pretty strong charge and actually arc and even kill people from the static charge just built up with it hanging in the air. So in order to prevent discharge inside the transformer, which may or may not harm the transformer, but it would certainly cause a pop every time it discharged, that 2.2 meg resistor keeps the static charge bled down. And of course we talked a little bit about the loop. Electrically, the loop is the same as a voltage generator and a resistance. That resistance is the resistance of the 14 gauge wire, a 3-turn loop, and the lengths of these pipes happens to work out to where each turn is 10 feet long. 3 turns is 30 feet. 30 feet of 14 gauge wire is still way under an ohm, so for the simplicity we can eliminate it from our calculations. And likewise, the distributed capacity between the 3 turns is going to be low enough to where the self-resonant frequency of the loop is way above the audio range, so we don't need to concern ourselves too much. The reason I chose 16 microhenries and a 1 ohm impedance is that at 12 kilohertz, which I'm using as my top frequency, that amount of inductance, 16 microhenries, will cause the loop to have its 1 ohm impedance. It'll be working into about 3.2 ohms on the transformer. So that means at 12 kilohertz the response will start to drop off, because the loop, it'll be up there around 1 ohm, and the load it sees will be about 3 ohms. So we'll have about 3/4 of the low frequency voltage. You get an octave or two below 12 kilohertz, say down to 3 kilohertz or lower, the actual inductance and impedance of the loop will have very little to do with frequency response.